The topic of formal languages and automata is a way of taking, let's say, like natural languages like English and Spanish, and trying to write a set of rules for either how sentences are laid out or words within the language are laid out. So, for example, suppose we wanted to have a vocabulary language. A vocabulary language is where we have a set of letters, right, the 26 letters of the alphabet. And then there are rules about how putting the letters in a certain order. There's no limit on what the size of the words can be. And then we're going to decide if this is a word that is within the language or not within the language. So, for example, we might have a function called English. Right? So I kind of wrote this out as like pseudo Java code. You pass in a word, and then we're going to make a computation, and we're going to decide, is this a word in English, and we're going to answer true or false. So we have to put some more interesting code, what I have in brackets here, but if the word is in the English language, we return a true, otherwise we return a false. So if we called English and passed in dog, it should return a true. It's a member of the language. If you put in XYZ, it should return false. That's not a word in the English language. So that would be like where we're taking the symbols, A through Z, picking some subset of them, arranging them in some kind of an order, and then running some computation that answers yes or no, if it's in the language. So, for example, we can decide maybe a simpler language could be something like this. Instead of having the 26 letters of the alphabet, maybe we'll only use an alphabet. We're going to use the letter sigma to mean the collection of letters in our alphabet. And maybe we'll use the letters A and B only. And we'll decide that our language, we'll call it language 1, consists of two words. The word AAB and the word ABB. All other combinations of all different sizes and orders are not part of our language. So we would have to create a function for our language that would take in, let's say it took in the string AAB, it should return true. If it took in ABA, even though it's 3 letters and only A's and B's are used, doesn't follow the rules of our language, which is it's either that word or that word. And so that should return a false. And if we put in AABB, that should also return a false. Our language. Okay. So to talk about languages from a formal point of view, if you think of languages like natural languages, like for example, a natural language like English, you could think of it from a vocabulary point of view, meaning you take a bunch of letters and arrange them in a certain order and you answer yes or no. Is this arrangement a word in the language? But you could also think of sentences where each component of the sentence are words separated by a space. And then all the words in your language can be arranged in any combination of ways, and you have to answer yes or no, is that a legitimate sentence for the language? So this is another language, but this is looking at it from the point of view of words and the way that the words are arranged. So instead of it being like letters like A, B, B, A, it's now a word and another word and another word. And we're going to ask ourselves if the words, the order in which they appear in the sentence, is that a legitimate sentence in the language? So for example, we can say the frog writes neatly. This is an example out of Kenneth Rosen's book. The frog writes neatly would actually follow English grammar, right? Because we have to have a noun followed by a verb, and then the verb could be followed by an adverb. So we could say, and this is what I call an article, the in front of the frog. So we could say the frog, and this is a noun phrase, writes neatly. Writes is our action, and neatly is an adverb describing how it writes. And this could be considered syntactically a legitimate sentence in English. Semantically, it may not, because frogs don't write. So maybe it doesn't have any legitimate meaning to it, but it syntactically follows the English language, the rules of the English language. So what we want to do, and many natural languages have so many rules to them that it would be impossible to write out all the rules. But what we'd like to be able to do is formally, if it's possible, sometimes it's not possible, formally write out the rules of the language, have an exhaustive list of all the rules. So for example, we could have a sentence like, the large rabbit hops quickly. And we're asking ourselves, is this a legitimate sentence in the language English? So what we can do is we can read over our input. So we're basically looking at input, which is, in this case, is a collection of words. And we might want to have a program that could read a word, read the next word, read the next word, and by the time it gets to the end of the sentence, it can answer yes or no. If the language rules are so complicated, we have to read words, and then when we get to the end, we have to say, okay, now what was before me? And if this goes in context with what's before it, then we could say this is a legitimate substantive of our sentence, and so on. So we could take a word like this, and we could read across and then say, okay, this is an adverb. So we substitute quickly with adverb. Then we can go and read again and say this is a verb. Then we can say that, here's our noun, and here's our adjective, and so on. And replace, at each pass of reading through the sentence, with what these are legitimate forms of, and then we can, once we finally get to the point where we have a verb followed by an adverb, then we could have a rule that says anytime there's a verb followed by an adverb, that becomes a verb phrase, so it gets rewritten as a verb phrase. And an article and an adjective and a noun becomes a noun phrase, and then anything that is a noun phrase followed by a verb phrase is a legitimate sentence, and then we can answer yes. So we may have to process this many times until we get an answer yes. So we would need a set of rules for the language. Well, first of all, here's a parse tree for the language. And basically we're saying a sentence, this is like a very simple version of English, but a sentence could be made up of two parts, a noun phrase and a verb phrase. And then a noun phrase could be made up of an article followed by an adjective followed by a noun. So the reason I'm saying this is a very bridged version of English is we have a rule here that you must have an article, which is not true in real English. Articles are optional. Adjectives could be actually a list of them, right? You could have the big, the large, hungry rabbit, you could go on and on. You could have actually an endless list of them. But here we're saying you must have one article, and you must have one adjective, and you must have one noun. And then a verb phrase could be a verb followed by an adverb. We can also put the adverb in English actually before the verb. It's optional way you want to put it. You could even construct sentences where there's some adverbs before the verb and then additional ones after it. And it still counts as a legitimate English sentence. But in this case, suppose we define a verb phrase as having exactly two parts, a verb followed by an adverb. It's the only way to do it. So then the large rabbit hops quickly could get parsed into a legitimate sentence in our subset of English. So for a language like English, and this is actually something you had to learn when you're a little kid, without it being explained to you, to learn to speak the language. The grammar for it might be, this is, again, a very small subset of English. In fact, it only has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 words in the whole language. But anyway, suppose we said that a sentence is equal to a noun phrase followed by a verb phrase. That is the definition of a sentence. Now we have to further define what is a noun phrase, what is a verb phrase. Well, a noun phrase is made up of an article followed by an adjective followed by a noun. Oh, in this case I actually made the article optional. And then I said or an article followed by a noun. I'm sorry, I made the adjective optional. I'm requiring the article but making the adjective optional. Then I'm saying a verb phrase is equal to a verb followed by an adverb, or just a verb, so I'm making the adverb optional. But again, I'm only allowing one. Now, for everything that is not explicitly like something you actually see in the sentence, but it's actually a component, it's made up of components of things that you see in the sentence, you have to further describe what these things are. So an article could be the letter A, or the word A, or the word the. An adjective could be large and hungry. So this is language that only has two adjectives, large and hungry. Nouns could be like rabbit or mathematician. Verbs can be eat or hops, and adverbs could be quickly or wild. So, when defining a language, we consider anything that you actually see in the string that you're parsing. We call these terminals. The lesson, these don't get broken up into smaller components. What's written in blue are considered non-terminals, meaning if you take a sentence and you break it into smaller parts, these smaller parts have to keep being broken down until finally you get to terminals. You have to keep breaking it down until you get to terminals. So the terminals are written in green, the non-terminals are written in blue. And then one of our symbols must be the start symbol, the thing that you eventually become, like a sentence. So for example, the hungry rabbit eats wildly, that will parse correct into a sentence. A mathematician quickly hops won't, because we don't allow adverbs before verbs. English does, but our little silly language doesn't. So this would not parse correct. And the large hungry rabbit hops quickly. Only has one adjective. Only one adjective is allowed. We put in two. So our grammar says that you can have an article, one adjective, and one noun, or an article and a noun. You can't have multiple adjectives. But in English, obviously, you can. Okay, so this type of thinking, you may not have realized this, but your whole life you have this kind of parsing thing, but you have every word in the English language. So it's a much, much bigger thing than you have over the course of your life. You learn to say sentences in English. Sentences that are correct and sentences that are not. Okay, so to write out rules for any particular language, we basically have a set of a vocabulary. So that could be a vocabulary, meaning a collection of words, or it could be a collection of words that you're going to arrange into sentences, or it could be an alphabet which you're going to take the letters of the alphabet and turn into words, like the two examples we've covered so far. So phase-structured grammar has the components we just went over. We have a start symbol, and then we say the start symbol is broken up into smaller components. Some of those components are actually, and it's typical to write small letters to mean the things that you actually see in the sentence, or the terminals, and capital letters to mean non-terminals, things that have to be broken down into smaller pieces. So, for example, we can have a grammar that says, we're going to start, the start symbol is, it starts off with a small letter A, and then it has a big X component and a big Y component. Then we further define the big X component, which could be an A, or it could be an A followed by another X, or it could be an epsilon is actually meaning an empty string. So this could actually be a series of A's. Like if we had 10 A's, you could say, okay, it's an A followed by an X. What is an X? Well, that's an A followed by another X, which is an A followed by another X. So it recursively defines itself. And then the last component, the Y component, is 2 B's followed by an A or 3 B's. So we define a grammar by saying we have a final, a start state. We have a final state, which would be at the top of our tree. And then we list out the components it could be, and then go anything that's a non-terminal, you define that broken down until finally it's broken down into terminal values. So a grammar has a vocabulary, has terminals, a start symbol, and then P is a set of rules, a set of productions. So that's like this. These are the productions. All of these lines. A sentence is made by these components. So this is how all the components get produced. So that would be a set of productions. So we can write grammars that way. And over the next, several classes, we're going to talk about different types of grammars. And sometimes they're referred to as type 0, type 1, type 2, and type 3. And sometimes they're referred to by their names. Recursively enumerable grammars, context-sensitive grammars, context-free grammars, and regular grammars. And from the point of view of, well, each of the 4 different types of grammars, the type 0 or recursively enumerable grammars, those are grammars where there's no rules on the productions. You can have any set of terminals and non-terminals on the left side of an arrow. Right? So, for example, the stuff that's on the left side of a production could be any combination of terminals and non-terminals, and the right side could be any combination of terminals and non-terminals. The context-sensitive ones are, well, like I say, we'll go over each of these in detail, but the context-sensitive ones are where you could have on the left-hand side, you can have an ordering of non-terminals, and then the right side would only would produce it if the non-terminals on the left side were in a certain order, or the context of which they appear in your sentence actually matters, makes the meaning. So an example might be in the English language, you could have sentences that have nouns, a noun phrase and a verb phrase, and the verb phrase could have a noun phrase, right? Like you could say, the mouse ate the bad cheese. So the noun is not cheese, the noun is the mouse, right?
Well, cheese would still be a noun, but it's a direct object.
But it's like a noun that's part of the verb?
It's receiving the action of the verb.
Okay. So, but in that sentence, there's 2 verbs, right? The mouse and the cheese. But the mouse...
You mean 2 nouns.
2 nouns, right. So, but what I'm saying is you can have an adjective, so you can say like the mouse ate the bad cheese. So bad is an adjective to the cheese, which is part of the verb. Is that, or part of the verb phrase?
I think it would be part of the verb phrase because it's receiving the action from the
right.
verb.
But if a noun phrase appeared after a verb phrase, then it would become part of the verb phrase. So it's the context where it appears in the sentence would actually matter what it becomes part of. So that's an example of what we're calling like type 1. Again, we'll go into more details. We'll focus on that type. But the type 1s are where the productions on the left side, the order in which they appear, determine what gets matched up on the right side. The type 2 are called context-free. That is where the productions on the left-hand side, you can have multiple non-terminals in a certain order where the order matters. On the left-hand side, you only have non-terminals. All the non-terminals are just one symbol by themselves, not put in a certain order, like a verb may have a noun phrase after it, which then becomes part of the verb phrase. Wouldn't have something like that. And then the most restrictive type, the type 3, or sometimes called regular expressions, are a grammar where whenever you have something on the left-hand side produces something on the right-hand side, you can have the right-hand side be a small letter followed by a non-terminal followed by a terminal on either its left side or its right side. We'll kind of show a proof that whether it's the left side or the right side, it's really the same thing. And so that's a more restrictive type. It's not a matter of matching up, like for a number of A's on one side of the terminal must match the number of A's on the other side, or the number of A's on one side must match the number of B's on the other side. So there wouldn't be any necessity to record any information about as we're reading. So yeah, like I said, we'll cover each of the 4 types of languages as we go further. Then the idea of a finite automator is, in the theory of computer science, but this also extends into natural languages. We could read a bunch of symbols, and if we're trying to decide yes or no, if a string is in our language or not, we would have, like we said with our grammar, we would have a start state. So that's the state where we start, and then we read a letter or a word, and then we decide if we're going to hop to a new state. And if we're going to have a language where we could read a word or a letter, decide what state we're in, read the next one, and when we get to the end of the word, we know at that point whether we accept this word or not. We don't have to go back and reread based on the context of where the letters are. If we can just hop around from state to state, not record any information about what we're reading, just bounce around from state to state, then that would actually be, the first language we'll end up studying is the regular languages. Regular languages have the property that we can read letters, and every time we read a letter, it determines what state we hop to, and then when we read the last letter, the final state we're in will determine if it's in the language or not. So a finite automata is just kind of a mental picture of a state that you start in. You start in a state, we could have many, many states, as long as it's a finite number of states. We can't have an infinite number of states. If there's a finite number of states, one of our states is going to have an arrow pointing at it coming from nowhere. That's the state you're starting in, so there should only be one of them. And every time you read a symbol, you just, whatever state you're in, for every letter in your alphabet, you have a transition to some other state, or maybe the same state. So this is a finite automata. It's a very simple one. It has two states. State one is the one that we start in. We could move over to state two, and from state two we could go back to state one. All the states that will answer yes, meaning yes, the word you've just read is in the language, it is a tradition to put two circles around it. That means the answer is yes. And if there's one circle, that means the answer is no. So what is this finite automata doing? We're starting here, and the language is apparently strings of zeros and ones, not A's and B's. And what we're doing is, if anytime we read a 1, we stay in the state we initially started in, which is an acceptable state. So I can see off the top of my head, if the word we're looking at, or the string we're looking at is 1, 1, that's going to be acceptable. 1, 1 will be acceptable. Every time I read a 1, I'm starting off in a good state. So first of all, an empty string is part of the language, because I immediately start here. So if I read nothing, I answer yes. I could read as many 1s as I want, and I'll always answer yes. But as soon as I read a 0, what happens? What does this finite automata do? It tells me if I'm in state 1 and I read a 0, where do I go? I go to state 2, which is now not a good state. Now from this state I could read again as many 1s as I want. And now I'm no good, no good, no good. Then if I read another 0, I come back to this state, now I'm good again. So what language is this automata trying to say yes or no to? So I'm starting at state 1, which is immediately good. So if I don't even read anything, I answer yes, that's a part of my language. So the empty string is considered part of the language. I can read as many 1s as I want, but as soon as I read my first 0, I'm now considered no good. And I could read a bunch more 1s, I'm still no good. But as soon as I read my second 0, now I'm good again. And then I can read a bunch of 1s and I'm still good. So what is this thing saying yes and no to? This would be the strings that have an even number of zeros. So if you inputted 1 0 1 0 1 0, it would go 1 0 1 0 1 0 1 0, and that would be considered good. As long as the number of zeros is even. So if you had 100 characters and it had 8 zeros in it and the rest were all 1s, it would end up in this state. So it's the language of zeros and 1s that have an even number of zeros in it. Okay. So let's look at a new language. And here we'll get used to some notation for languages too. So let's say our alphabet is the 2 letters A and B. And we want all the words that start with exactly 2 A's, then have a set of B's where there's at least one B, and then followed finally by an A. So we could write it out, we could kind of write out a grammar if we wanted to, but we could also depict it like this, just saying language 2 is equal to AA followed by B, and we kind of raise it to an exponent, and the plus sign means that there's at least one. If there was a star here, it would mean it could be 0 or more. This means 1 or more, and then followed by an A. So for example, the language AABA should be true. That's one of the words in our language. ABBAA is no good for 2 reasons. It didn't start with 2 A's. The multiple B's is okay, and then it must end with just 1 A. After the last B, only 1 A. So there's actually 2 violations here. And then AABBBA, this would be true because it started with 2 A's. We can have as many B's as we want as long as there's at least 1, and then it must end with an A. So that's a word in our language, in this language, language 2. Okay. If you wanted to write code, so here's where like we're going to try to take the concept of natural languages and computer science and try to overlap them. But if we wanted to write code for that language, we could have a variable called state. That could be a string, and we set it to the word good. We read a character, and if it's not an A, we change the state to no good. Read the second character, if it's not an A, we change the state to no good. So we're checking for an A, and then we're checking for another A. Then we can say, let's read at least one B, and if we don't read a B, then we're going to say we're no good. Then we can have a loop, reading over and over and over. As long as you keep reading B's, just stay in a good state. As soon as you do not see an A, then, if it's not an A, then you go to a bad state. So we could read as many B's as we want, and that's fine. As soon as we read a non-B, check that it's an A. And if it's not an A, we say we're no good. And then if we finally get to the end of the file, we just return the state, and the answer yes or no. So this would be kind of a program doing it. But theoretically, what is our program doing? So here's a finite automata for this particular language. We're starting at this state. We're starting here, we haven't read anything yet. If we read an A, we go to a state that's still not acceptable, but we've read our first A. We have to read 2 A's, then maybe a series of B's. And then, so we read our first A, our second A, then we would read at least one B. This should be an A. This should have a loop of B's. We should read as many B's as we want, and then finally end with an A. And the idea of what a trap state is, this is a state that if you ever enter the state, you can never transition out of the state. So it's implied that every letter in the alphabet takes you to this state. So if you ever enter the state, your word is no good. So sometimes we call that a trap state. And the idea is if we eventually end in a double circle, that means we have a good word. After we read our last A, if you have any A or B after that, that makes our word no good. Okay. So then there's the idea, if you wanted to write a computer program for a language, so you give it a word, it runs a program, and the program then answers true or false. It's a sentence or a word in your language. Versus a finite automata. The finite automata is just kind of the way your mind is laying out what the program's going to do. And then depending on how complicated your program gets, will you be needing memory to write results along the way so you could go back over your productions and reevaluate them? Or do you not need memory? Do you need limited memory? Do you need a lot of memory? Is going to determine how complicated the language is, and those are the 4 different types. The type 0, 1, 2, or 3 is going to be based on how much time and memory you need to perform your computation. So any language that can be determined by a finite automata, which is basically you have no memory, you just have a finite number of states, you read a symbol, you move to another state. You read a symbol, move to another state. You just keep bouncing around from state to state. When you read the last symbol, whatever state you're in determines whether you answer yes or no. So any language that has that property, that it can be depicted by a finite automata, is considered a type 3 or regular language. So some notation for languages would be, the idea we use the exponent. I thought that was a little confusing the first time I saw that. An exponent means how many times the letter appears. So A3 means 3 A's. A star means 0 or more A's. So it could be no A's or 6 A's or 100 A's. A plus means there's at least one A and maybe even many more. We could use the or symbol, so this means that the next letter to appear in your word is either A or B. So then we could put brackets around an A or B and put a 3 up here, and then this is any combination of 3 letters that are any combinations of A or B's. So it's exactly 3 letters and any combination of A's or B's would be carried. Okay. So an example of a regular grammar, and again, this is not really a talk on regular languages, but we want to talk about formal languages and finite automata, and finite automata happens to depict regular grammars. So for example, we can have a language L is equal to all words that start with an A, and then are followed by BA star, meaning I can have 0 BAs or 1 BA or 2 BAs or 3 BAs. So A, BA, 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 BA is in my language. And we could write the grammar for this. So again, this is terminals and non-terminals. We have a start symbol, and we say every sentence in our language, or every string, starts with an A and then has something after it which we have to further define. So it starts with an A and then it has this thing after it, and here's the thing after it. So that would be like in our English case, we would have, a noun and a verb. So this would be something that has to be broken down into smaller parts. The next thing would be a BA followed by one of those things again, which could be another BA, followed by another BA. Or it could be an epsilon, which means the empty string. We needed a letter to mean nothing's there. So epsilon means the empty string. And this is a left linear grammar, meaning every time we have a non-terminal, a capital letter, becomes non-terminals, terminals followed by non-terminals. The terminals are always on the left side. They're never on both the left or the right or just the right side. All non-terminals are on the left side of all terminals are on the left side of non-terminals. You could also have a right linear grammar, where you're just putting them on the right side. So these two grammars would be identical for this language. They look different, but they're identical for the language. So we could have an A, and then we could have an X symbol with a BA after it. And we define the X symbol as being an X symbol with a string of BAs after it. Okay. Then the idea, this will come up a little bit later on, but the idea of enumerating a language. Suppose, for example, we have the same language. So we have the language L, which is an A followed by a string of BAs, BAs, and BAs. We could write a recursive function. So a recursive function is a function that makes a call to itself. And we could write code that can print out the entire language. Now wait, does this make sense that this is an infinite language? So this is a language where all the words start with an A, and then could have any number of BA, 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 BA after it, off to infinity.
It has to be together.
Right, they would always have to be in order. So if we ever had like 2 A's in a row, that's no good. So for example, A is in our language, A, BA is in our language, A, BA, BA is in our language, A, BA, BA, BA. And it goes off to infinity. So this is an infinite-sized language. And we can actually write a program that calls itself. So I'm going to enumerate. I'm going to start with a string. I'm going to start off. Well, I can originally call this thing with the letter A to print out my first word. So I print out A. And then I add a BA onto the end of it and call itself again. So I pass in ABA. It'll print out ABA. Then add a BA on top of that and call itself again. And this would run, this would now be an infinite loop, right? because it keeps calling itself and it never stops. But it would enumerate the whole language. So if I ran this, it would run forever, and it would print out every word in our language. So this is a way of recursively, calling the function recursively, and I'm enumerating, printing out the whole language. So I'm recursively enumerating a language. Okay, so when we went back, very early, sorry about that. We did define the type 3 one, so that would be like the first, our first type of language we'll cover in our class. So, some courses go from 0 to 3, some go from 3 to 0. The regular languages on the top, the type 3 languages, are the ones where you can answer yes or no if a word or sentence is in the language using the least amount of computer equipment. And the type 0s are the ones that need the most amount of computer equipment. And the best names for the type 0s are recursively enumerable, meaning you could write a program that will infinitely, run infinitely and print out every word in the language, but that's probably the best way to describe those types of languages, so that's what they call those. So I kind of wanted to just kind of go from the beginning to the end in this talk. So by the time we finish studying all of these types of languages, what we'll realize is that the regular languages can be depicted by a finite automata only, with no memory. And as you're reading each character in your word, or each word in your sentence, which is really the same idea, you don't have to make any recording of what you've read in the past, you just have to maintain what state you're in. When you finally read the last character, you can answer the question yes or no if it's in the language. The next type is going to require a limited amount of computer memory. So we're going to read a letter, bounce to a state in our finite automata, but we also have to record some data about what we read, because it may have to match up something later on in the word. Then the ones that are considered context sensitive or type 1, we're going to require a lot more computer memory, maybe memory that is big O of the size of the input. So if you make the input very large, the amount of memory we're going to need to do the computation would have to be proportionally as large. And the type O's are pretty much unlimited. We may need unlimited space, unlimited time to decide whether or not the word is in that language or not. Okay, so so we'll cover, go over properties of each of these and what strings are in one set, not in the